back to the day 2 of ICRACM 2024. Now, let me invite the session manager for this session, Dr. Sayan Kumar Pal, Assistant Professor in the Department of Physics at the CVV Institute of Science and Technology. Over to you, sir.
Thank you. Hari Om. Good afternoon. I heartily welcome everyone for the 8th keynote session of the International Conference on Recent Advances in Composite Materials 2024, organized by the Institute of Science and Technology, Chinmaya Vishwavidyapith, deemed to be University, Kochi. First of all, I request all of the participants to follow a few guidelines for the smooth conduct of the session. Please ensure you are muted during the talk, and I encourage you to really delve into the proceedings of the session and post your questions in the chat box, which will follow after the address. Let's make the most of this unique opportunity to engage and widen our knowledge in the field of biomaterials. So it gives me great joy to introduce now our esteemed speaker, Dr. Binsi P.K, for the 8th keynote address. Dr. Binsi P.K began her career in 2009 as a scientist at the Indian Council for Agricultural Research, Central Institute of Fisheries Technology, better known as ICAR, SIFT, Kochi, where she is presently the senior scientist of the Fish Processing Division. She specializes in marine biomaterials research, in which she has authored numerous research articles, edited books, and contributed chapters in reputed international publications. Dr. Binsi holds multiple copyrights and design registrations under the Intellectual Property Regulations framework of the Government of India. Importantly, she has developed technologies for 4 biomedical products, which were subsequently released by the Honorable Union Minister for Agriculture and Farmers' Welfare, Government of India. She has received several awards, starting with the University Gold Medal from Bangalore Agricultural University. In 2016, she was honored with the Professor Hiralal Chaudhuri Medal for Excellence in Innovative Research by the Zoological Society, Kolkata. In 2022, she was named the Best Fisheries Scientist by NESFA Tripura, and in 2023, she received the prestigious Professor H.P. Shetty Award for Excellence in Fisheries Research from the Asian Fisheries Society. Dr. Binsi was also awarded the Naib International Fellowship in 2014 for her foreign deputation on smart packaging techniques at Rutgers University, US. In the same year, she also received a fellowship from the prestigious Alexander von Humboldt Foundation, leading to her work in Potsdam, Germany. Dr. Binsi serves as a scientific expert for over 65 companies across India through consultancy agreements with ICAR SIFT. She has mentored numerous master's and PhD students in biomaterial development and is an active member of several national committees and scientific panels. Without further ado, I enthusiastically invite Dr. Binsi P.K for delivering the 8th keynote address of the ICRACM 2024. The title of today's address is Bridging the Gap, Translational Research in Marine Biomaterials for Tissue Regeneration. Madam, I invite you for the talk.
Thank you. Thank you for the nice introduction. Good evening, all. Let me share my slide first. Hope I am audible.
Yes, you are very audible. Clear.
Yeah. After the excellent talks, the previous talks, I was here on the platform. It was a very, eye-opening talks in many aspects for me. But the topic which I'm dealing today is a bit different. It's more of biological science. So you'll be thinking what a biological scientist is doing in an engineering conclave, which is more of engineering parameters dealing with. Probably I opted this topic, that is bridging the gap, translational research on marine biomaterials for tissue regeneration, is rightly because translational research is totally a multidisciplinary topic, or it requires intense multidisciplinary approach. When I started my work on biomaterial, I realized that I cannot just end up a product taking it to the market shelf just by knowing what the material is. It requires a long journey. That is, I may require a chemist, I may require a physicist, I may require a statistician, I definitely require a data analyst, I require an engineer, a process engineer, I require a marketing specialist. And the list as such, it goes on. Probably that is the reason when I was contacted to give a note in this platform, I thought this is the right platform for me to talk on translational research. Since it's the fag end of today's session, let me straight away go to the topic. Just I tried to Google around what is the status of translational research. It gives me a figure of around 50 lakhs, 20,000 results. When I gave biomaterials, again, it gave me a figure of 14,90,000. When I give marine biomaterials, it is trimmed to almost like 1,38,000. That means almost 10% of the biomaterial research. I clubbed translational research and biomaterial. The figure is again trimmed down to around 13,000. Coming to translational research plus marine biomaterials plus the very key word in this talk, that is tissue regeneration, I got around 10,000 or 11,000 research. So this itself shows that there is a huge gap from translational research to marine biomaterials or tissue regeneration. The figure is drastically reduced from 50 lakhs to around 11,000. Here comes my first research or the first work, that is the natural hydroxyapatite. Of course, as introduced, I'm working with Central Institute of Fisheries Technology, where our mandate is to work on fish and related to fish. So I started working on fishery waste management. So in that one, I got several bones, skin, scales, entrails, viscera, etc., which is all dumped into our natural water bodies. Our market is flushed with so much of waste material, and it is all dumped into the open water bodies. So I started analyzing the individual materials like scale. This is a scale. You see, under microscope, it appears like this. That is, the top one, what is there is the collagen fibril. You may be knowing what is collagen. Collagen is a connective tissue. That is our body's total protein content, almost like the majority of the major protein is collagen, which is the skin is composed of collagen, our bone is composed of collagen, the enamel, the tooth is composed of collagen. From top to bottom, if you see, from head to our nail, our capillaries, our veins, our nervous system, everything, our internal organs, everything is made up of collagen fibers. Along with that, in scale, what you can see is another compound, that is hydroxyapatite. Again, the bone, tooth, all the hard part or hard tissue parts, that is again composed of collagen and hydroxyapatite. Hydroxyapatite is the mineral phase and collagen is the protein phase. So here you can see the enamel. Enamel of tooth is composed of more than 90% out of the hydroxyapatite, whether it is from fish or calf or pig or anything. The bone or tooth, it is made up of hydroxyapatite, which is very much similar to the hydroxyapatite, what is seen in fish scale or fish bone. So dentin, you see, it is more than 70% is composed of hydroxyapatite. Human bone, 60 to 70% is composed of hydroxyapatite. So this itself tells what is the significance of this hydroxyapatite in tissue engineering or bone engineering. See, if you have a defect, this is osteoporotic bone. If you have a defect and such a defect in the bone where you have a crevices, appearance of crevices, you can keep grafts in this one, right? So the best or the most ideal material for this type of graft is the hydroxyapatite itself, because the body won't be recognizing it as a foreign material because it's chemically composed of the same thing as the bone. So here we can think of making hydroxyapatite graft that is derived from fish scale or bone like that for as a graft material here. Similarly, if our tooth enamel is made up of hydroxyapatite, then why can't we use a capping material as a hydroxyapatite that is derived from fish or the bone? That is the major output, or that is one of the major observations that we have made through our research. This is the hydroxyapatite that is prepared by our team and that was released as introduced. It was released. Just see the cost of production. See, 1 gram of the same thing. It is a 0.5 gram. This is a commercial one just for introducing the product I made. I just kept this one. This is a 0.5 gram pack of 4. That means around 3,000 rupees. That means per gram, it is almost like 1,500 rupees. And the approximate cost of production of hydroxyapatite from fish scale. This is hydroxyapatite that we have made from fish scale. It is around 360 rupees per kg. See the margin, very low volume, but high margin product. It goes directly to the medical industry. So every fish bone or fish scale that we have dumped into our common water bodies, that has to be measured in terms of 1,500 rupees per gram. See the quantity that we have already lost. This is one parameter that some parameter that clearly says that you can remove the collagen. You can either extract collagen or you can just remove collagen by incineration. So as per our technology, we extract collagen because that is the most sustainable approach that one can tell you. Because both collagen and hydroxyapatite is coming from the same material and both are of high medical or nutraceutical value. So why can't we extract collagen so that what is remaining is hydroxyapatite? We require a minimal heat treatment to make it as of medical grade. So when I say medical grade, this you can see it is heated from 600 degrees Celsius to 1,100 degrees Celsius, where we got the optimum temperature as 1,000 degrees Celsius. So from here itself, what is there on the spongy-like material is collagen. So when you heat it, the collagen is incinerated, it becomes puffy and it is escaping. So once it escapes, you get clear-cut pores in this one. This is the porous structure. So we have standardized this one based on AFM measurement as well. And you can see a clear-cut changes in the UV visible spectra itself once we go from lower temperature to higher temperature. This is very important parameter that the surface area and the pore diameter, you can see it's been increasing. See from 2.34, it's been increased to 4, 5, and up. So here also the porosity is being increased. So what we require is microporous, not nanoporous, even microporous. So this is the one what we have got. See, this is microporous as well. There is another parameter is that there should be interconnections between the hydroxyapatite crystals. So that gives the correct bond strength when you use as a graft material. So this is how we have got, and this is a very apt material that we have standardized for our further studies. Here we see this hydroxyapatite we subjected to biogenic activity. That means when you put it in a simulated body fluid or when you use it as a graft, what happens is the graft material will be slowly, it will be disintegrated or it will be removed from the body and disappeared from the body. And in that place, the new bond will be regenerated. That will be our own bond. So the graft will be replaced by our own body bone. So that requires intense mineralization, remineralization again. So that is what is found here. You can see the crystals of hydroxyapatite here and there on the one what we have already put. This is how it has been shown. Here again, we have to conduct a series of toxicological studies just to claim as it is suitable for medical purpose, because medical purpose, pharmacological research, it requires a long time of clinical research. So we have started our research with the subcutaneous implantation. What you can see is this the 4th day, 8th day, 12th day, 16th day. By 16th day, what we are expecting was a settlement of the immune responses. So immune responses, what here you can see is a settlement of immune responses. Some were here you can see, and this is the hydroxyapatite what we have given. And you can see infiltration of the fibrous tissues here and you can see the infiltration of fibrous tissue. That means the new bond or the collagen part of fibrin forms the initial part of the collagen, or it is the pro part of the collagen, and it has been collagen being synthesized in the graft material. So this is a promising result for us, and we have continued the research that we could find that foreign body giant cell was not at all detected. That means the immune response was satisfactory. There was no chance of rejection. The chance of rejection by the body is minimum. And you can see the very dense network of collagen or the fibrin tissue network here. This work was further we started with bond regeneration aspect. Here we have tried for the alveolar ridge regeneration aspect. Here also cytotoxicity assay on osteoblast cell lines was analyzed. So what we could find that cytotoxicity was minimum. It was not showing above, or it increased the cell viability and the proliferation of the cells, osteoblast cells, and macrophages also showed very good biocompatibility. So these are the standard requirements to use as a graft material for bone regeneration, some of the things. So here also scratch assay, we tried just to see that what is the regeneration capacity or the cell proliferation capacity of the graft that we are going to put. So here also we got that it promoted the cell migration, and it showed promising result at 400 microgram per ml. So this enhanced migration is very crucial, as I said, because the graft has to be somehow replaced by our own bone cells. So that part is clear here, and it was giving good results. So again, it went to the histological study. Again, we have compared with the untreated control group and the oseograft. Oseograft is the commercial one. We have compared with the commercial one that is available in the market, as well as our own FSHA means it is a fish-derived hydroxyapatite. So here it is almost like 35 to 40% of the original FSHA graft material was resolved over a 4-week period. In 1 month, the first month is almost like 40% was resolved. Then approximately 50 to 60% by the next month too. So this was matching with the standard requirements of using bond graft material. We moved to the 3D printing. So here we have incorporated the PLA as well as along with that. This is just to increase its biodegradability aspect and to give a strong matrix for hydroxyapatite to stay. So these are the parameters that we have standardized, and this is how it looks. So this is the pores that is very much visible because, as I said, the porosity and the interconnections are very much required. So these pores were maintained throughout with hydroxyapatite. Also, you can see the hydroxyapatite deposited in the all over along the PLA graft material. So this is how it looks like, and we have then the compression studies and found the values of 13.4. It is almost like megapascal, which suggests that it is not very much suitable at the moment. It is not very much suitable for a hard bond, but it is it mimics the human cancellous or trabecular bonds, so soft bonds, and it has got the required porosity and cell, which favors angiogenesis, cell migration, and the proliferation, as I explained. So in vitro toxicity also, we have confirmed that it is not toxic. And this is how it has been. The toxicological studies, it showed that even after 72 hours, it was showing the satisfactory or the minimum cytotoxicity when compared against the simple PLA. So there was no aggregation of cell. This is a hemocompatibility. So no aggregation could be found in the samples on intubation. And all the morphological features were well maintained. There was no cell rupture or any other thing we could find in this. So as per ASTM standards, they were hemocompatible and hence can be used at sites in contact with blood. That was our conclusion of the study. This is a published data. More details can be, we can get from the paper itself. So there are some more other parameters in detail what we wanted, that is tissue response score. There is a score analysis. So what you can see is the cell response score is all minimum. It is lesser even than PLA for PLA hydroxyapatite. That means the tissue response, immune response, the cell response, as well as the tissue response. It was found to be minimum or lesser than what is, that is against the PLA. So, it shows that 1% below hemolysis has to be below 1%. So that is also, it was satisfied. This is a histological analysis again. What we have found is this is after implanting the graft. So we have taken samples and 2, 4, and 8 weeks post-implantation. This is corresponding values for PLA, and this is the corresponding value for PLA hydroxyapatite 1. So reactivity score compared to the PLA, that was almost like 0. That means it was even it was not giving any adverse immune responses compared to the PLA. So even in vivo analysis confirmed the biocompatibility of the scaffold, which is very much similar to the PLA, is already well-studied material and has to be and is a non-biocompatible material. So that is why we have taken PLA as a matrix. This is so since it is an engineering conclave, I just thought of adding one more slide other than tissue regeneration aspects. So similarly, we have standardized the material for heavy metal removal. Same thing with PLA and hydroxyapatite. Here we have got for uniformly porous filters and the gradient filters. So it was that structure, that filter structure was maintained throughout. That you can see. This is a very close-up picture of the same thing. You can see the distribution of hydroxyapatite throughout. It is there throughout the core as well as to the shell. It is uniformly distributed at the outer as well as the inner wall. This is the picture image showing that one, and it was analyzed against. We have used lead as well as the cadmium, and what we could find is this is the one. with HAP, the cadmium was showing higher than the lead. This is, I'm not detailing those aspects. That paper is also published, probably you can get. So this material, it has gone to the hands of entrepreneurs. So that we are happy that we have involved so many scientists. It's not from a fisheries scientist alone. There was the contribution from, as I said, there was contribution from chemists, physicists. There was a medical professional involved in this one. There was statistician, of course, statistician was, so it is a multidisciplinary approach that has taken the material to the market. Here you can see the one in the market as well. Another one probably of interest to this platform may be the carbon nanodots. I think I've seen a couple of papers also in this one. So I need not explain what is carbon nanodots to this platform. I'm just telling that it is having very much similar core as the graphene structure. That itself says that how precious this material. So what all I'm telling you, please remember that it is connected to fish processing discard or the same fish market waste that we usually come across, which is dumped or which is on one side, it is just neglected and piled at one side of the market, creating a lot of issues to the public. So these things are generated from what all I said, even the hydroxyapatite or collagen or the carbon nanodot. This is all coming from this simple waste material. So as you can see in the market, carbon nanodots, it's almost like 20,000 rupees per 10 ml. So it has got the advantage or the uniqueness is that it has got multiple functional group inside. It is a graphene-like structure. So here you can see it's a most functional, the reactive functional groups such as carboxyl, hydroxyl, and the amino groups. So it is definitely having the application in medical imaging, catalysis, LEDs, and sensing functions, antimicrobial activities in food industry, etc. So this is the carbon nanodot. This is also published in recently. So this is the original one. It looks like, and when it is subjected to the fluorescence, this emits the fluorescence. So this is how, and it is it's very much in nano size, 4 to 5 nanometer. So this is from fish scale again, then prawn shell, then fish skin. See, this all was giving the blue-green photoluminescence. See, UV spectra, which is very much characteristics to the fluorescent one, the photoluminescent one. Here, this is the FTIR spectra, which is confirming the graphene structure, conjugated C double bond, C conjugated aromatic rings, as well as the OI stretch, everything which we were talking about, which is distributed over the shell structure, is very much visible. So lambda max at around 220 to 260. Which is typical for graphene structure, and it was confirming the same thing. Just for your interest, one more thing to adding to the slide, that is, it's a very good carbon nanodots are very good corrosive, imparts very good corrosion resistance. So this can be very much used as an anti-corrosive material for the metal surfaces. So my interest is to use as an anti-corrosive material over bone implants or the implants, which is basically the titanium implants like that. So we just tried it on. First one as the marine building board steel. So which is the most susceptible material for corrosion because it's in the subjected to the marine environment. So if carbon nanodots can prevent the corrosion of the marine steel, definitely it has got application in the body fluid as well. So we have tried this one. So usually marine steels, you know that it's been protected by epoxy polymers, and there are certain hardness commonly employed are the amine-based hardness. So CD contains multiple amines. So that is the beauty of CD. It contains multiple amines, so it can act as a synergistic filler. This is our hypothesis, and this is what expected from this one. So we reinforce the epoxy polymer with the CD, and it was coated over the board building. So we have done this, confirmed this work with the several nanodose that is being prepared from different materials, not only from the same, but from the different. This is the difference, epoxy-coated marine steel CD. This is a control one that we usually do. This is a commercial, the usual practice, and this is the one reinforced epoxy-coated marine steel. So this is here we have used CD. You can see it's a very smooth surfaces, and there was no crevices, bumps, or nothing. It was very smooth. So our assumption was pure something like it act as a filler between the material and it reinforced. So the pore size was reduced. That means the infiltration is reduced. The contact with the metal is reduced. So if you give a coating of such a polymer, which is hardened by a CD, so you can minimize the contact with the outside material or the body fluid. Here also, polarization, resistance, and corrosion potential, we have analyzed. So what we have found is it has significantly reduced the corrosion, improved the resistance to corrosion. So this was also confirmed. And another one, which I at the beginning of the slide, I just mentioned the collagen, or another one is the collagen peptide. This is a hydrolyzed form. We have a facility to pilot scale facility at CFT to extract all these materials, collagen and collagen peptide. So again, this has gone to multiple entrepreneurs. We have made a composite of collagen as well as the CD. So what happens is, as well as hydroxyapatite, since it's for bone regeneration. So for bone implant, like titanium implant, we give a coating with this one, and we expected the same result of filling the material, minimizing the contact between the metal and the body fluid, and improving the cell attachment. So this was the expectation for us, and we could find that it is working here as well. So it was almost like everything, it works as it, because it reduces the contact, and being a natural material like collagen as a part of bone, hydroxyapatite again as a part of bone, CD, it acted as a compatibility material, like it improved the compatibility of the metallic implant with the bond matrix. So that was a good observation we could find. It was still on the research arena, and has to be further, it has to be, a lot of research has to be done on the same material. So another one, this is all what I'm explaining is all collaborative research. I'll tell you, this is again the catechin as a functional additive in electrospun PCl gelatin nanohydroxyapatite nanocomposite fibers for tissue engineering applications. So here catechin was used as an antimicrobial. So you can see this is the fiber material, what we have electrospun, and this is the one fiber matrices. You can see with the addition of nanohydroxyapatite and gelatin, the size is being increased. This is because nanohydroxyapatite is being incorporated into this matrix. So catechin was used as 2%. This is again subjected to bone regeneration studies. This is the material that is being implanted, and it was switched, and this is the immune response that the cells surrounding, on the tissue surrounding the matrix that was isolated week 1, 2, 3, and 4. You can see there was no signs of inflammation here. You can see this is the one PGL, the signs of inflammation actually it was reduced. So here and all, you can see this is as the concentration was increased, there is simultaneously, it was gradually decreasing. So cellular structures all appear normal, no evidence of degeneration or cellular infiltration. So this is a skin sensitization test again. we have tried on different material. So erythema and edema was also, it was comparable, the test and the control was all comparable. We didn't find any additional edema responses in our material or the scaffold implanted rats. Again, toxicity, heart, liver, and kidney that we have found no apparent signs of inflammation, necrosis, or of other abnormalities. It all appeared very much normal to the control. So this is, as the concentration increased, this is how it was behaving. So that also shows that it is very much compatible with the material. So moving to the next one, chitin and ketones, and it's a very well-known material for all of us. So we have a separate process lines that we have standardized. CFT has standardized. It's actually, I should say, CFT has pioneered this work from years long back. So, and we have a very standardized and optimized technology. The major issue with chitin, ketones, production is it's an environmental issue. So because a lot of material is being pumped into the ETP. So that is one of the major issues. So we have our own standardized, our own protocol that is very much minimizing the environmental issue and reducing the ETP load. So it was almost like 1/6 of the conventional protocol that is being generated. So we have tried this one. Again, it is a collaborative work. We have tried chitosan also as an implant coating. So we could find the cell viability was comparable very much with that of the control, is as well as the cell attachment. As I said, it's very much important. The cell attachment assay gives you very much important information about the cell regeneration, tissue regeneration. So after 72 hours or so, it showed almost a steady increase in the number of cells that it has been replaced, or it has been, the cells are compatible with the material surface. So again, the corrosion resistance that was also analyzed here in this paper, that also explains the different things. So that also imparted better corrosion resistance by giving a coating of chitosan. Another, probably, I would like to introduce one more material which is of having very high potential in bioengineering. This is marine melanin. Melanin is actually, the black pigment that is seen even in the squid or the cuttlefish ink. You can see even in our body. The black pigment is the same thing of our hair. The black coloration that gives you the hair, the black, that is the melanin pigment. So this is one of the study that we have conducted. We have applied this melanin coating upon hair. So hair appears like this under the microscope. The control hair, it appears like this. So when we expose this one to UV almost 100 hours, so what we can see, there is a clear cut, a rupture along the shaft. So this one is a UV induced damage to the hair cell. We coated melanin over the hair cell, and this is the untreated one, which gave you a crack. This is the one which is coated with melanin. You can see it is very much intact and it is very much similar to the control hair. It shows that this is a very good UV protective agent. So you can think of multiple possibilities, huge potential of this material and material fabrication. So this is a very interesting observation that we could get it. And another important one is astaxanthin. So this is one of the material which is very much important because this astaxanthin is the reddish orange pigment that is found in shrimp shell. We extracted it from the shrimp shell waste, and this is a wonderful antioxidant and anti-UV, UV protective too. So anything that is having antioxidant, anti-inflammatory properties, definitely it has a role in tissue engineering. So because a lot of inflammatory responses can be expected once a material, a foreign material, is inserted into your body. So this can be minimized with a sequential release of antioxidant material or anti-inflammatory material. So here comes the importance of astaxanthin that we have found that it's beautifully, it is reducing the inflammatory responses. Even in HeLa cell line, it is giving wonderful result that it is very much, it is controlling the cervical cancer cells. So what we could find in normal cells, it is improving the activity of cell proliferation. Whereas in cancer cells, it is reducing. That means it has a focus targeting of cancer cells active. So this is again, it's a plus point for us. So this result, I think it has to be taken very much forward. And this is some of the product that we have released by the Union Minister and our Director General of ICAR. So what probably to conclude or to say that we have several products in the market, biomedical products or the nutraceutical products or the health products, healthcare products, personal care products, everything. But majority is occupied by the imported ones. We have the resource, we have the expertise, but we don't have the product, our own product in the market. There are several reasons. We cannot list out everything, but there are several reasons. But the only thing what we have to think is the potential what we are having is numerous to bring more the country origin products in the market. So what we have seen in recent years is maybe because of the translational research, what has been carried out at different sectors of the science. So we ourselves have noticed a huge increase in the inquiries and the technology adoption. This is a small segment, I'm telling you, this is a small segment from my own team. So just imagine how much we all together can bring out. This is a very small effort. This could bring out this much of technology adoption in the country. Definitely, the sector as such will be turning from an unorganized sector to a totally evolving industry. That probably none other than this is my takeaway points. That is, translational research may be hectic, it may be challenging and full of unexpected twists. But rivers are as vast as the ocean. Once we see our own product in the market, the enthusiasm and the joy that we are getting surpasses all these hectic challenges and expected twists. So that is the beauty of the thing. And it's totally a multidisciplinary play. Success demands a fusion of expertise, scientists, engineers, medics works in harmony to create breakthroughs. Definitely, there is a huge gap in the translational research and marine biomaterial. We have to harvest that one. We have to cross the boundaries of countries and continents, and sometimes venturing beyond the known limits of science. Sometimes an idea by a layman may become crucial. So we cannot underestimate, or we cannot set a boundary of the collaborators. It can be a scientist, it may be from a layman too. So it's totally a multidisciplinary, and we have to cross or join our hands together. So I sincerely thank all my team members, Dr. Nebu George Thomas, Dr. Yogesh B. Dalvi. Nebu George Thomas, he is a dentist. Dr. Yogesh B. Dalvi, he was involved in all the animal studies. Dr. P.M. Ashraf is a chemist. Dr. Ritvik Aravind is an engineer. Dr. Ranish Balakrishnan, he is a physicist. So this is the small team, the work that we have, what all I have presented is a collection of the effort that they all have contributed. Thank you, one and all.
Thank you very much, Dr. Binsi P.K, for your wonderful talk on the marine biomaterials for tissue regeneration and its translational advancements happening in this domain. and the future possibilities it can generate. So thank you very much. Next, I think it is time to open the floor for having some questions. So I kindly request the audience to post your questions in the chat box, and we will try to answer them one by one. Okay, madam. So we are having a couple of questions. I'll
Yeah.
read one by one.
Yeah, please.
The first question is from Nivedita S. Nair. The question is as follows: what factors affect the long-term stability and performance of marine biomaterials in clinical applications such as bone regeneration or drug delivery?
Specific mechanism contribute to the, pardon, which one?
Yeah, I'll just repeat.
Yeah.
So what factors affect the long-term stability and performance of marine biomaterials for its applications in bone regeneration or drug delivery? What are the factors that
Yeah.
will affect the long-term stability?
Yeah, there are a lot of factors that affects these two, which you have pointed out is a right keyword, that is the long-term stability and performance. The first thing is the compatibility itself. The material has to be very much similar to our body components. So the first toxicological process confirms all those things by compatibility. The test which I have mentioned that clears all those things. So naturally, what happens, the nature gives you a similar composition for maybe if it is for human being or if it is rat, as I said, if it is calf, or the only thing is the composition wise, the quantity may be different, but the material almost remains the same, which I said, like collagen and hydroxyapatite, when I say it makes the majority or the composition of the bone, it works for human bone as well as for the animal bones, or maybe for the rat bones. Anything, it works the same. The only difference is that the crystallinity may be different between the rat bone as well as the human bone. The arrangement may be a slightly different. The porosity may be a slightly different. The strength may be a slightly different. So that defines the performance of these materials in clinical applications. So what happens is, if I'm extracting the material from a fish, I have to make it or fine tune to human. So there comes the importance of this translation. There is the major work that is involved in the translational research. So we have to see long-term stability. Stability is, again, it can be engineered. Stability, what material, what we are getting is in the fine powder or in the native form. So we have to manipulate, which we said in PLA composite, it has the same thing. So if you want to make an artificial, it's actually artificial one, even though the components are natural, it's ultimately it's an artificial one. So you have to mimic the properties of the target one. If I'm using, even if I'm telling it is for alveolar bone, the properties of the requirement is different. If I'm telling a skull bone, it may be different. If I'm telling a thigh bone, it may be different. So the major role is engineering these properties. So that decides the performance. I think I have answered the question.
Yes, surely.
Yeah.
So I have another question from Mr. Sarath Tiar. How do the properties of marine-derived hydroxyapatite compare with synthetic and other natural hydroxyapatite for bone grafting applications?
Yeah.
So how it compares?
Yeah, we have synthetic counterparts for this hydroxyapatite that is being already there in the market, and that's being widely used for the applications. But when you come to a natural component, as I said, it ultimately goes to our body. So the body should realize it as a natural component. So the crystallinity or the ratio of the calcium and phosphate, and there are several types of natural hydroxyapatite, like carbonated hydroxyapatite, fluorinated hydroxyapatite. There may be some other metals like magnesium incorporated. So what happens is the natural may be connected with some of these elements, but synthetic may be the very pure crystals of calcium, phosphate, but natural never it will be. It will be associated with some carbonate or non-carbonated or the magnesium like that. So what we are deriving from marine organisms, it's very much similar to the natural one, hydroxyapatite of human bond. That is one of the things. Second thing is the biodegradability, because the synthetic hydroxyapatite has a major drawback of very slow degradability. That limits the new bond regeneration. So as I said, the graft what we are putting, impregnating, has to be replaced by our own material, our own bond cells. So if the degradation is slower, that means the bond regeneration also will be slower. So it has to be replaced. So this is one of the major challenge that we were facing. We had to make it as per the standard requirements, and we could find that within 3 months, our hydroxyapatite material was almost like it was replaced. So that biodegradability we cannot expect with synthetic hydroxyapatite, what is available right now in the market. So I think this is clear.
Okay, thanks. So if there are no more questions, we can thank once again Dr. Binsi P.K. for joining us today to deliver the keynote address for the International Conference on Research Advances in Composite Materials 2024. Thank you to all the participants for attending the session. Have a nice day. Thanks.
Thank you.
Thank you.
Thank you.
Thank you. Thank you, Doctor, for coming and delivering a wonderful talk.
Thank you. Thank you, Dr. Praveen.
Thank you. Thank you.
Yeah.
And dear participants, we came to the end of the keynote 8, and after this session, from 5:15 to 6 o'clock, so this platform is open for discussions. So